Let's give a big round of applause for the Carbon Removal Challenge 2023 finalists. I'm Matt Parker. I am the co-founder of the OpenAir Collective. I'm also an associate professor of the arts here at NYU at the NYU Game Center. Yes, we have a Department of Game Design here at NYU. And in a way, the Carbon Removal Challenge is a big game to try to get people excited about saving the world. We are here to honor the finalists from that challenge who came up with the most interesting, innovative, hopefully world-changing designs for this challenge. We got a great international cohort of people who participated in this challenge and a great international cohort of finalists. I'm standing up here talking about this. You're gonna hear from the finalists, but all the teams that participated in this event deserve your thanks and applause. So let's do a quick round of applause. This has been a dream for OpenAir for a long time. We had 28 teams from 10 different countries, from 5 different continents, be part of this challenge. But tonight we are here with the 5 finalist teams. But I do want to thank, there are countless people to thank in this challenge, and I'm going to leave some of them out, and I apologize if I do not say your name directly. But I do want to call out a few members of the OpenAir team who especially contributed to this challenge. Particularly, I'd like to thank Grant Faber, Duncan McDowell, Richard Chen, Natalie Brazington, Owen Bell, Jet Valinga, sorry Jet, your last name is tough to say, Samir Heber, Logan Clare, and Winnie Song. So much of what you see up here is their work, and we could not have gotten here without them. I'd also like to thank our sponsors, especially the teams that made this possible, the sponsors that made this possible, the NYU Alliance for Public Interest Technology, who provided the funding to get these finalist teams here from all around the world, NYU Sustainability, NYU Tisch, Brink Air Company, and Peter and Erica Reinhardt. Without their generous support, we wouldn't have been able to have these teams here. We wouldn't have been able to provide them with the resources that we have and with the hopefully the options that they're going to have in the future to take these nascent ideas, these early stage ideas, and have them become startups, companies, world-dominating, world-saving ventures. We also have a group of incredible partners, so many organizations that, honestly, I was blown away by how many people are willing to support this. I can't name them all. You can see their images on the slide behind me. You should all go to the challenge page for the OpenAir Collective and visit all their websites. They did do some amazing work. But there are some people here right now. One of our partners, who I do want to bring to the stage right now, we have Alex here from Carbon Upcycling, who 3D printed the awards for the Carbon Removal Challenge that our teams will be getting tonight. They don't know about this. This is a bit of a surprise for them, so that's going to be a cool moment in a little bit when they get these awards. And we have 3D printed awards for them that are from biodegradable plastics, or some of them are made partially from captured carbon, a new kind of filament that actually is made from carbon captured from the atmosphere. So Alex, why don't you come up and talk a little bit about carbon upcycling and these awesome awards?
Thank you. Thank you all for inviting me. I'd like to thank Matt, Duncan, and the OpenAir team, first of all, for organizing all of this and giving the next generation this opportunity to work on some really cutting-edge projects. So the metals, as Matt was saying, carbon upcycling, we have a consumer brand, OCO, and sorry. And so this filament, this 3D filament that we made, is about 10% recycled carbon, and it boasts some insane strength and thermal properties. And you know, we thought it was fitting that for the 2023 Carbon Removal Challenge that the metals be made of something with carbon capture technology. So, thank you all very much.
And with that, we're going to get right into our finalist teams. Who's excited? Yeah, let's make some noise for these teams. We're going to start with our winner for Best Visionary Plan, Monash Carbon Capture Conversion from Monash University in Melbourne, Australia. Come on up, team.
Hello everybody, and thank you so much for having us on this beautiful evening here in New York. So as mentioned before, we are the Monash Carbon Capture and Conversion student team, also known as MC Cubed, coming to you all the way from Melbourne in Australia. So our team was conceived actually about 1.5 years ago, and we work on 6 different projects, 3 of which are looking into carbon capture and 3 of which are looking into carbon utilization. And when we were thinking about something that's been embedded into our team mentality right from the beginning is how do we integrate our carbon solutions? It's equally important, I strongly believe, to think about the technologies independently and to think about, what's their efficiency going to be like, where are they going to get their resources from, but also to think about how are they going to work together? How are they going to be integrated into our communities? So the project that we really put forward for the purpose of this competition was how are we going to integrate all 6 of our projects? So we have 2 streamlines, I guess you could say. The first is focusing on the biological side, and the second is more of a synthesis streamline. And so I'll hand over now to Joe, who will just work us through the beginning of our biological pathway.
Cool. So just to show Maddie's great graphic she drew for a bit of maybe just like overall context as well, just to see mentally how everything could fit together. But back to microalgae. So microalgae is the beginning of our biological-based solutions. Essentially, what happens is microalgae grows. And as it grows, it captures carbon dioxide via photosynthesis. And that happens in microalgae at a greater rate than in many other plants, which is really exciting. And what we can do is try to optimize the growth of the microalgae to try and catch as much carbon dioxide as we can. So what we're trying to do is design a floating photobioreactor, which we store the algae in, and what we're going to do is put it in the ocean. That's for a couple of reasons. So one is so that we can use the motion and the energy of the waves in the ocean to mix the microalgae, and the other is for temperature regulation. So these combined benefits both mean that there's a reduction in the energy required to grow the microalgae. To complement this, we're also designing and running experiments to figure out the optimum growth conditions of the microalgae, including things like light variation, pH, how much carbon dioxide they really like to grow in. And we're trying to use that information to implement it into the design of our photobioreactor. So when we get the microalgae, we grow it, we then harvest it and we dry it out, and we've got all this microalgae. What are we going to use it for? Our team has a solution. I'm going to pass you off to Jen to figure that out, to discuss that. Thank you.
Thanks, Joe. So as Joe was saying, so we've got our microalgae that has captured the oceanic carbon dioxide, and we want to be able to store that captured carbon for a long period of time, and with that we want to make useful products or process the microalgae into useful and valuable products that are able to store this carbon. So currently with our work back in our home base in Melbourne, we take that microalgae and we process that into biochar through a method called pyrolysis. And the value in this biochar is that it's able to store the carbon or sequester the carbon for a period of 100 years or more. And also it's able to be used in an abundance of applications. One such which we focus on is in the agricultural industry, where the biochar can be used as a soil applicant in order to improve soil health as well as promote carbon uptake in plants. Also, with the microalgae that we use as a feedstock provides a major benefit in that it can enhance the carbon capture and carbon conversion efficiency. So now I'll pass it on to Nick, who will discuss the forestry aspect of our EID solution. Thanks.
Thanks, Jen. So forestry, we're obviously looking at growing plants, and to do that, we're looking at using 4 plant species. So to this end, we have sweet forage sorghum, empress trees, and 2 separate species of bamboo. These are intended to be intercropped in an agroforestry approach, with the aim of storing carbon in both the soil and the plant biomass. To assist with this, we use biochar from the eco-industrial district to both improve the growth rates of the plants that we're using and to facilitate cost-effective and long-term soil carbon storage at rates much greater than is achievable just by using plants. We selected these plants on their ability to grow in poor soils, but more importantly, their rapid growth rates. Now, this rapid growth rate improves the cost efficiency of the program, and it increases the rate at which carbon can both be stored and at which value-added products can be produced from the woody biomass that we produce, which improves the cash flow of the project, creating a financial incentive to capture carbon. Now, with our solution, we also aim to provide a few environmental benefits. Specifically, agroforestry supports biodiversity, as well as improving soil, air, and water quality much more than traditional agriculture does. Currently, we are undertaking controlled greenhouse trials, growing sorghum in the presence of biochar, and this will hopefully help us to evaluate how our solution performs in practice rather than just on paper, and help us to orient our work moving forwards. So now I'll pass over to Charlie to outline what we actually do with the woody biomass once we've produced it.
Thanks, Nick. So the construction industry is widely known as hard to decarbonize due to the reliance on concrete and steel, with each sector contributing around 8% to global CO2 emissions. So our approach to alternative sustainable building materials is a new engineered timber that is based on cross-laminated timber, or CLT. So CLT is made by gluing layers of timber together and generally oriented so that they are perpendicular to the adjacent layers. So due to the lightweight yet high tensile strength of bamboo, we propose a bamboo composite CLT, or BCCLT solution. The concept is similar to CLT, however, we incorporate bamboo in specific layers. So our team is investigating how we can alter and improve the strength and stability properties of BCCLT by changing certain specifications such as the number of layers, the thickness, the adhesive effects, as well as the orientation of each layer. So that concludes our 4 biotech proposals, and I'll pass it over to Jaden, who will cover our 2 synthetic approaches.
Thank you, Charlie. So Maddie and I will now briefly go over the synthetic approach that we have to carbon capture and utilisation. And in short, we are using a aqueous modular direct air capture system to capture the carbon dioxide directly from air, and then we send that carbon dioxide over to an engineered flow cell, which then converts the CO2 to a product called ethylene through electrolytic reduction. So modular DAC systems, or small DAC systems in layman's terms, they're relatively underutilized and underexplored in the research, and that's because of the high energy penalty currently associated with them. And MC Cube's direct air capture team have identified this as a space where there's real opportunity for novel developments to be made, especially as this is a space where developments that drive down the energy costs and increase the energy favourability of these systems can really allow for an accelerated deployment of direct air capture in urban environments and HVAC systems. So currently, to do this, we are using a modified evaporative air cooler as our contactor. The schematic is sort of presented up there. And to do that, it's modified to enhance the solvent circulation and also to optimize the air solvent contacting. So if you look down here in the bottom left, the air, or actually even up the top, the air flows in with containing CO2, passes over the packing material, and then saturates that solvent. And then we send it off to a Tudic apparatus to analyze the absorption properties. And we're currently also looking into the utilization of bioproducts from the biotechnical teams for as an energy source, a sustainable energy source for solvent regeneration. And I'll pass to Maddie to go over the ethylene production.
So you may be asking yourself, well, what are you going to do with all this captured CO2 from your DAC units? And I've asked myself the same question. Now, typically what we often like to do is a process called geological sequestration, which essentially just means pumping it underground and forgetting about it. Now, that is a stable solution, but I can't help but ask myself, like, is there something more creative and more innovative that we can do with this CO2? So what we're looking into is converting the CO2 into ethylene. Now, I should note there are many different molecules you can convert CO2 into, and we chose ethylene particularly because ethylene is the building block for polyethylene, which is our most commonly used plastic, and plastic is an incredibly valuable resource for us, despite its many downfalls, which I'm sure we're all familiar with. So our project is focusing on this thing called a flow cell. I've got a little one up here. They're quite small. Obviously, ideally, we're trying to scale them up. And there's a diagram up here that shows, at a very basic level, what's going on in there. So for me, my team, we're focusing on a number of different things with this flow cell design. We're looking at things like, how do we develop the catalyst? How do we think about the overpotential? What geometries will best promote the efficient conversion of CO2 into ethylene? So our approach is multifaceted and has to address a number of different questions because this technology has so many different components to it.
So what Maddie was saying brings us to what we view as our team's greatest strength, which is that our multifaceted and broad approach really offers a great platform for students, undergraduates in particular, to work on finding solutions that matter and to getting experience in the sustainability field. Additionally, we like to think that our overarching approach encourages us to consider and appreciate how carbon solutions need to exist together and must be integrated to find sustainable, future-focused solutions to combating climate change. So that's all we have today. Thank you very much for your time and focus. And if you have any questions, we'd be happy to field them in the reception afterwards. Thank you.
Time for the medal ceremony. Start with the largest team first, I guess.
Thank you. That's it.
Yeah, it is.
Yeah, all right. Let's bail. Grab your laptop, Jay.
Thank you. Thank you, Monash. So not only did they receive those very cool awards that we spoke about before, they also got Carbon Removal Challenge bags, t-shirts, soap from our partners at Clean O2. That is soap created from captured carbon as well in their little goodie bags there. So some carbon removal swag as well. So our next project are winners for most detailed project, and that is the Viridian team from University of Waterloo in Waterloo, Canada. Viridian, please come up.
Hi everyone, we're Team Viridian from the University of Waterloo in Canada. We're very excited to share with you what we've done for the carbon capture project. So this is our team. We're an undergraduate team of interdisciplinary engineers from the University of Waterloo, and we're associated with the And we span programs from chemical engineering, mechanical engineering, and environmental engineering. And because we're associated with the Engineers Without Borders chapter at the University of Waterloo, we also have a lot of support from our general members on different portions of the project.
So before we start to talk about some of the science and kind of our decision making, we just want to give a good outline of our design. And so we're working on a direct air carbon capture, utilization, and storage system. So if you look at the diagram above, the yellow portion is kind of the process overview for the air. So it's direct air, so we're starting with just ambient air input. And so this is relatively higher CO2 than what we would have at the end. And we're using a sorbent, which is amberlite. And in order for the sorbent to work effectively, first the air would need to be dehumidified and then compressed. It then passes through the amberlite, which absorbs some of this carbon. And then you have air out, which is at a lower concentration of CO2. Once this amberlite is saturated, it then the carbon needs to get released. And we do this through just pumping through distilled water to create CO2-enriched water, which can be used as an algae feed. This helps the growth of microalgae, which can be then used as a valuable product. And one thing I also wanted to note is, in particular, we're investigating the efficiency of using a fluidized bed to store the amberlite. And so essentially, instead of having your sorbent on a filter and some other mechanism, you can kind of see the GIF over there. Your amberlite is a small white powder, and you're hoping to agitate it through this compressed airflow. And also have more surface area exposed so you can have a greater efficiency. So like we just have a small demo. So at first you'd be, imagine if this is your little amberlite particles, you're just passing through regular air, getting it full. Once you've noticed that you've reached the saturation, then you can pass through water. You'll have a bit less fluidization because water is a lot heavier. But in this stage, you're releasing the CO2 into this water stream. So this is what the actual setup looks like in real life. So I guess to my left, you have the actual capture cycle. So this is where the air is coming in. So you have your air coming in. It gets dehumidified through both active and passive dehumidification methods, compressed and then put through our bed or fluidized bed, which is that syringe in the middle. From here, the release cycle is all done on the right, where we have our water and our pump. So I'm going to pass it back to Laurel.
Yeah, so I just wanted to share a little bit about why we chose these two substances. So in addition to the obvious carbon capture abilities of the amberlite and the sequestration abilities of the algae, we also found that there was a lot of compatibility between the two, and that this was something that we wanted to look into further. So as Hussein mentioned, when you have the wet cycle happen of washing the amberlite, you end up with this CO2-rich water, and we wanted to aim to design this with a closed-loop concept in mind, so having the waste product of one system being the input to the next. And so that kind of led us to this thought for algae, and the algae is compatible with this because it requires the CO2 to be already dissolved in water for it to be sequestered, so it was a very natural pairing between the two of them. And then when you look into it further, they actually also both need dechlorinated water because the chlorine will clog the active sites of the amberlite, and it's also obviously going to kill the algae, so it's compatible in that way as well, and that's something that kind of drew us to the two substances. Yeah.
So now we want to look at the results of our system. But before we look at the result of our system, we want to look at the amberlite. So before we look at the amberlite, we mentioned how we processed the amberlite through a chlorine oxidate solution where we would sodium carbonate, my bad. Sodium carbonate solution where we would activate the amberlite. So the overall absorption preparation process in our system resulted in a volume increase of 98.16%. And from this indicated successful matrix enlargement of allowing the amberlite to bond with the carbon dioxide. With this proof of concept system that we created, we were able to capture 76.6 parts per million of carbon dioxide, which translates to 14.3% of efficiency over a 5.5 minute cycle. And if we look at from this, we want to also look at the energy efficiency of our system, because we can capture as much amberlite we want, we can capture as much carbon dioxide we want, but if we don't look at the energy consumption, this means nothing. So right now our system is about 50 kilowatt per kilogram of carbon dioxide captured, but this is due to the fact that a lot of our products that we're using was off the shelf, and these off the shelf products wasn't made for what we need our system to do. So with clearly defined ideal conditions that we want, we can re-engineer solutions specifically for our system and improve this overall energy efficiency.
Over the course of the project, we faced a lot of design challenges, a few of which I wanted to go into today. So one of which was we needed filters that retained the sorbent within the syringe. So in order to do so, we had a few different requirements for the filter. First, that it had to be malleable such that it can fit in a circular tight space. And second, that the pore size within the filter was less than the sorbent, which obviously to retain the sorbent inside it needs to be smaller, but not so small that it restricts fluid flow. This would be an unnecessary energy drain, so we definitely did not want that. Because of these reasons, we went with mostly cloth-based solutions, and I think mesh material 1 on that side is what we ended up going with. One of our other design challenges was that we needed some custom tubing adapters because we were noticing a lot of fluid losses between when the junction point when we changed from the tubing to the syringe or the tubing to the pumps. So at those junction points, they were not standard sizing, so we went with 3D printing. At first, we tried plastics, so PLA and PETG, and when we noticed that there were still leaks within the print layers and at the ends of the print, we decided to go with a resin-based solution, which best fit our needs. And third and finally, this is something we are currently working on, our algae growth experiments, because we want to be able to grow the algae in the best possible conditions. So one of our biggest design challenges there is that we don't want to dilute, when we add the CO2-enriched waters, we don't want to dilute the nutrient mix such that it's not beneficial to the algae. So how do we control that is one of our problems that we are kind of experimenting with ratios, but also algae needs light and agitation to grow. So what are the ideal conditions there to kind of get us the best possible solution? So that is underway.
Okay. So Njia kind of touched on some of the next steps there. So in the really short term, we really want to start experimenting with the algae samples we have. We need to develop a control and then actually develop more of the CO2 enriched water so then we can test it and see how much better is the growth and just validate that against all the theoretical data. I think there's a lot of work we can do in terms of the automation of the system as well. We have all of our inputs from our sensors. If we're able to automate to kind of trigger that wash cycle at the appropriate time, we can run these tests a lot more efficiently and quickly, collect more samples, and get really more robust data to verify this chemical process. So that's kind of what we're thinking for the immediate next steps, technically. We also really have a goal to inspire some of the students at our school to carry this on forward. So we're also doing a lot of planning as to how we can make sure this is an initiative that really continues and is enjoyable for a lot of people. We all get along, we had a lot of fun working on this, but we really want to put some thought into how we can make this enjoyable and meaningful, for incoming first years and for everyone who wants to get involved. And so this is a really core part of our next steps as well. And so we'd just like to thank, OpenAir, NYU, our Engineers Without Borders, our design team, and of course University of Waterloo. And thank you for your time.
Yeah, glasses off. It's probably a good idea.
Thank you so much. Our next team is our winner for Best Immediate Business Plan, Spark Semi-passive algae-rooted carbon capture. How's that for an acronym? From Drake University, from Des Moines, Iowa.
Yes, thank you, thank you.
Yay! Okay.
Hi, everybody. Can you hear me all right? Up? Oh, this seems right. Yeah, let's go with this. My name's Tyler, and I'm with the Spark team from Drake University. In? Here? All right. So my name's Tyler, and I'm with the Spark team, which stands for Semi-Passive Algae-Rooted Carbon Capture. And we'll kind of get into what that means as we go along. But essentially, we designed a buoy. So we were trying to figure out what we wanted to do for this project and decided that algae might be the best approach for carbon capture directly. And so what we decided through looking at the research is that there was many approaches we could take. One primary facet that's often used in algae research with carbon capture is promoting the growth of algae. And a lot of this is done primarily with AI or design systems that rapidly circulate algae. But another way to kind of increase the net carbon capture is by decreasing the amount of energy put into the system. And so that's the approach that we wanted to go with. And so with that, we looked to our own community for solutions of what would be a great way to grow algae with minimal input. And as Iowa is an agricultural state, there is a big problem with fertilizer runoff causing nitrate and nitrite pollution in drinking water supplies, particularly the Des Moines and the Raccoon River. This data right here is actually from the Raccoon River, which is a primary drinking supply of the entire city of Des Moines. Now, as you can see, the nitrate levels are a bit variable. They're highest in the summer, which works out great for algae because that's when water's the warmest and algae likes to grow the most. And so for our purposes, that's great. Environmentally, that's somewhat catastrophic. High nitrate levels actually lead to a phenomenon called algae blooms, which are a situation in which algae growth goes uncontrolled, and it leads to the death of almost everything in the ecosystem, as well as eventually the algae, which not only is an ecological catastrophe, but as that algae decomposes, releases a lot of carbon dioxide into the atmosphere. And so we took this information and this ecological problem, and we realized that if we were to grow algae in a river polluted with nitrate, it would actually promote the growth of algae using pollution that already exists, while also capturing carbon from the atmosphere. And as this design actually takes no input energy aside from making the buoy itself, which I'm assure you is not too much effort, we actually have pure carbon capture, as any algae that's grown is carbon that's captured from the atmosphere. And so with this, we have our own fertilizer. It's using the natural currents of a river or a fresh body of water to churn the algae. And this is well scalable because we can have as many of these as we want. The design is fairly simple in itself. We have a primary chamber which would contain the algae inside the buoy. Above that, we have a dome, which would be transparent. It would allow sunlight to come in from all angles and channel it inside the buoy to get maximum penetration of the light into the algae receptacle. Beneath that, we'd have a filter. This is a nanopore filter. 1.2 microns is just small enough that Chlorella vulgaris, the algae that we've been using, can't actually pass through, but nitrates and other nutrients from the water can diffuse up through it. And water can pass into the buoy through pores at the bottom, which, if we want something to float, would also require us to have a flotation device at the top. This design has multiple benefits. The first and foremost is that it is carbon capture. As the algae grows, carbon dioxide is removed from the atmosphere, which was the goal of this challenge and our goal when designing this buoy. When converting the carbon dioxide to biomass, you do have biomass that you then have to deal with. And so there are 3 ideas that we had of where this biomass can go. The first is that it could be dried and used as a fertilizer. As I said, Iowa is very agricultural, and so not adding more fertilizers into the environment would be a benefit. Algae can also be used as a dietary supplement, and this was actually the idea we were most excited about. When it comes to having algae, most people don't really think about eating it, but as you dry it, it can be a very valid protein dietary supplement for humans or livestock, which would reduce carbon emissions from transportation of other dietary supplements into the Midwest in particular. As well, the city of Des Moines especially, with the nitrate problems in the drinking water, have been spending a lot of money and expending a lot of energy in the process to remove nitrates chemically from the water. With this buoy requiring no energy input and purifying the water, the energy that would be expended would actually be negligible. And so the carbon dioxide that's caused, the emissions that are caused by the denitrification process would be eliminated as well. And as a third benefit, as we are essentially channeling algae blooms in each of these buoys, we're actually reducing overall algae blooms as nitrate levels fall in water. As well, we wanted to make this a community-centric solution, and so we wanted it to be scalable from an entire metropolitan area or even on an individual farmer's land. And so this buoy that we have designed actually cost us $80, and we were buying everything from scratch. There are many opportunities to use recyclable materials and actually cause the price of this buoy to go down significantly. As well, it can be homemade. We wanted this to be accessible to as many people as possible, and with reasonable hand tools, you can make one of these buoys all by yourself and put it in whatever body of water you would like to purify and capture carbon with. And finally, it works on multiple scales. Whether it's that single farmer or the metropolitan area, we can have different sizes of buoys, different shapes of buoys suited to any particular body of water. So we have a prototype of a 5-gallon drum over on the side, but there's no reason why this design couldn't be continued with a 55-gallon drum or some other major design.
Thank you, Tyler. So in regards to future development, what are the areas, perhaps, in which the buoy can be improved upon? Well, for one thing, we did notice while testing that there is the issue of when do you know when the algae is done with its growing period, and afterwards, when do you remove it? Such a question is somewhat answered by a pre-existing water buoy by the University of Toledo, which uses algal bloom sensors in order to detect when algal blooms are within the Great Lakes. Such a device can be brought down to a smaller size and fit within our own buoy. And as can be seen in here, such a top lid, such as a hinge or screw top, can be used in order to remove the algae once it's done with its growing period. Because the current design of the buoy is designed so that one person can potentially make it, a simple design like this would be able to, so a farmer who is designing and controlling this himself within a lake would be able to detach it, remove the algae, replace it, no problem. Additionally, one element is that Chlorella vulgaris as an algae species is not able to tolerate a wide variety of temperatures, mostly cold. We discovered this because while using Raccoon River water, it was winter. We had 1 week to test this. So ultimately, in order to solve that problem, a solution could be that there is no design alteration to the buoy itself, rather a alteration to the algae, so that we either genetically alter Chlorella vulgaris to tolerate higher temperature differences, or find a different algae species that is able to tolerate that. So there is many different ways that the buoy can be developed in the future in order to create a brighter future. Because it is a simple design, we are able to go in many different directions, whether that is improving the algae, improving the buoy, or developing an energy-based system so that way it can be more efficient in the future. So that is why I believe the future is bright with this spark buoy. Thank you.
Your heads seem more.
Thank you.
Thank you. Oh man, I am so excited, and honestly, a little sad. We only have 2 more teams left. We're coming towards the end now. Our next finalist is the winner for Best Engineering, SWAN, Synchronized Water Amine Nexus from University of Victoria in Victoria, Canada.
Hello, we are from the University of Victoria in British Columbia, Canada, and this is our SWAN direct air capture unit. In the next few minutes, let us take you under our wing and introduce you to SWAN. Oh, that's one. So this is our team. We have Darian, Amar, Satria, and myself, Jasmine, and we're part of a multidisciplinary engineering team at UVic. So why carbon removal? As we know, climate change is a continuously growing issue that needs immediate attention, which includes implementing carbon removal methods. Our club, the UVic Renewable Energy Club, or UREC, started a few years ago to create a space for students to get their foot in the door of renewable energy and other related sustainable initiatives to gain some experience before they start their careers. We were inspired by the OpenAir Collective's mission to facilitate a community-based approach to tackling the climate crisis. We wanted to reflect that element of accessibility to a wider audience in our project. I'll let Satria explain the goals we set forth to achieve.
All right, so our group created several goals here. So first is to create an easy-to-build design. This is so that we don't require much technical knowledge in order to design our unit. And the next one is, in order to create that easy to build unit, we'll be able to maximize readily available components. So we wouldn't need components that need manufacturing or further processing. Also 1,000 versus 1. By this, what we mean by this is actually our group envisions a world where we have 1,000 or even more units, small units of the SWAN unit, compared to one singular large unit. And so where people can are able to see in the real world what they've produced and see that they're able to make a global impact, compared to one large unit where they really haven't participated or really haven't taken part in. And so through this, we would like to introduce our SWAN unit, and we'll have Darian give a brief overview of the unit itself.
So what is SWAN? SWAN stands for the Synchronized Water Amine Nexus, which we chose because of the resin that we're using, which is amine-based. SWAN is our carbon removal project designed to capture CO2 directly out of ambient air. In this design, we achieved our goal and managed to use almost entirely off-the-shelf parts or 3D printable parts. SWAN uses a moisture swing-based approach of carbon capture where the resin beads capture CO2 when they are dry and release it when they are exposed to moisture. The SWAN has 4 main subsystems that comprise the system as a whole: the reactor, the air system, the wetting system, and the electrical system. Satria will start us off by explaining the reactor and air system.
All right, so this is an image of the reactor and air system of our SWAN unit. So within the reactor itself, we have sorbent cartridges that enclose the sorbent for CO2 removal. The infrastructure of this reactor itself was made through like 3D printed parts and components that you can find through your local hardware store. It is also modular and scalable. As you can see, the sorbent cartridges are attached to a bar, and you can easily insert more sorbent cartridges based on what your team needs to capture carbon. Also, simply there's just a fan to blow ambient air through the system and blast gates to separate the air, depleted carbon air and also carbon-rich air from the system itself. And so in simple terms, we're blowing air into the system, we're letting the sorbent cartridge do its magic, by desorbing and absorbing CO2, and then we're also having air exit through our blast gates. I will let Amar talk about the water system.
Okay. So as Darren mentioned, SWAN works on the basis of moisture swing. Therefore, we need a watering system to enable this process. And in SWAN, we have equipped really small, inexpensive, like easy to obtain micro irrigation heads that you can install, and they are installed on this 3D printed frame. The frame looks a little complicated, but trust me, it's just squares and rectangles and triangles. What we plan to do is have this all open source. So all you basically need is an internet connection, just download the files and then have a 3D printer that you can print them on. And it's exciting now that we have 3D printers that can actually capture carbon dioxide in them. So it's something we can possibly look into as well. But yeah, other than that, to actually circulate the water, we have some RV pumps that we've installed, and this creates a closed water loop where we just have the reservoir, this drum, that contains water. It has to be distilled water because the sorbent it tends to get damaged if you use just normal tap water, for example. So the idea is the pumps take in water from the reservoir, circulated through the reactor, and then back in, making it a self-sustaining system that is really easy to automate. All right, I'll pass it on to Darian to speak about the electrical system.
So like Aymar said, we wanted to have this device be able to run in an automated way. So what we did is we got a microcontroller and had it hooked up to a bunch of relays so we can control the timings for the pumps and the fan, and basically test around with different like timings for how long a washing cycle is or a drying cycle. And we have two CO2 sensors to measure ambient and the outflow, so we can adequately measure our like CO2 that is being captured. And we also are logging this data so we can basically analyze this and adjust values based on like humidity and temperature of the ambient of the environment, so we can have it be a better CO2 sink.
So for the techno-economics of our SWAN unit, this chart here, it shows a price breakdown of how much cost was allocated to each of our subsystems. And as you can see here, a lot of our costs are dominated by the sorbent system and the structural system. A point to note here is that this is in initial development, so we are hoping that with a little bit of refinement and a little bit of tinkering, we can get the total cost of this unit to a fraction of ours, at least, once this can be set out as a reproducible package. We have the system cost per kilograms of CO2 captured as $2 per kilogram. This was obtained from our peak load capacity, and then we distributed it over a time period of how long we thought our SWAN unit would run for. That's how we got the metric. And also, as we mentioned in our goals, we want to create a design space. So this idea is out for anyone. Anyone wants to make improvements, make this better. They have more creative ideas than us. They're free to go and use it. But yeah, so that was the idea.
So it is the future of SWAN. So at this point, we're still prototyping and testing, and we've done testing on the subsystems individually. So the next immediate step will be to integrate, test, and optimize the system as a whole. We're also exploring options for what we can do with the captured carbon eventually, including greenhouse enrichment and opportunities to collaborate with student teams at UVic and beyond. The main thing is that SWAN is just the beginning. We are hoping to provide a starting point for people that are interested in getting involved with carbon removal and to help people's ideas take flight. So we'd like to thank the rest of our team, shown here, all of our sponsors, and OpenAir for making this opportunity a reality. So thank you.
Next year, longer ribbons, I think, is the first note I'm going to put. But I think it's worth it just for the comedy. All right, we are down to our final presentation. Our winners, and I'm let's just, before we do the final presentation, let's just give a huge round of applause for everybody who's presented so far, all the people who worked to make this possible. Finally, our winner for Best Literature Review and Research is the CO2 electrolyzer from Indian Institute of Technology, Bombay, from Mumbai, India.
Hello, everyone. Am I audible? Hi. Thank you everyone. Thanks a lot to the OpenAir Collective for inviting us in here, and it's really an honor to be present among all the the solutions providers. It's a very much a privilege, I would say, that's there. I represent basically the team from the DST-sponsored National Center of Excellence in Carbon Capture and Utilization at IIT Bombay in India, and also a brand new startup that was incubated last month called Urja Novak, which is providing clean energy and net zero solutions from the group from IIT Bombay. And most of the student participants could not make it here because of the time constraint, but then I'm thankful to all of them who have joined here, and we basically want to present you our solutions on novel ways and rather low-cost, sustainable solution for carbon dioxide capture, conversion using the CO2 electrolyzer, and then storage in the form of mineral carbonation. So I'll invite Arnab to talk more details about it.
Thank you, Vikram, and good evening, New York. Just ensuring everybody's awake, because I'm from India, so I'm still traveling in Indian time. So when we look into this carbon dioxide problem, we found that carbon dioxide is here from the beginning of the Earth, and it is a part of this photosynthesis respiration. So how that becomes a problem to us? And when we look closely, found that carbon dioxide is good when it's in balance between photosynthesis and respiration. But when we are actually putting more and more carbon dioxide than the plants or the algae can take out, that is a problem. And in the just last year, we put 36 billion tons of extra carbon dioxide into the atmosphere. And that carbon dioxide is getting accumulated in the atmosphere. That is the problem. So our thought process was very simple. Whatever the extra we are putting in by human beings, we human beings has to take the responsibility and remove it. So how to do that? So the thing is that carbon is not a problem. Problem is carbon dioxide into the atmosphere. So don't just let the carbon dioxide go into the atmosphere. Capture it before it escapes to the atmosphere and convert it back and bring it back to this cycle over here, which can ensure, just give me a minute, which ensures that the carbon dioxide can be captured. And now we have two ways: either put it back where it came from, mostly from the fossil fuels under the ground, put it back there, or convert it into some chemicals, which we are actually using in a huge amount every day. For the first part, we actually develop how we are going to capture carbon dioxide. And some of my friends provide very unique solutions. We also came up with a solution that, can we use water to capture carbon dioxide? Basically, can we make soda water? The answer is yes, we can do that, but the carbon dioxide solubility in water is quite limited. So how we can improve it? So over there, we have developed a unique catalyst which can improve the concentration of carbon dioxide in water. And once we capture that, nobody first believes that. How do we know there is carbon dioxide in the water? It is colorless, odorless. So we have mineralized that captured carbon dioxide to calcium carbonate, and that calcium carbonate ensures that, yes, there is carbon dioxide into the atmosphere that we have captured. And this calcium carbonate that we have captured, it is very much useful for the industry. It's a $1 billion industry. We use it every day in multiple industries. And that can be utilized what we actually captured from the carbon dioxide. Next, when you're looking into, not all the industries or all the people are looking for mineral as the end product. So they look for, is there any other product we can build? And the answer is yes, we need other chemicals. So what are the other chemicals we can come out? So we can produce methane, natural gas. We can produce polymers, that is very important. We can produce methanol. And we can also produce carbon monoxide. So when we first come out with the carbon monoxide, is it really carbon monoxide we use daily? The answer is yes. And then when we do the market research, we found that not only we use carbon monoxide, but it is one of the largest used carbon material in the world. We used it every year close to more than 4 billion tons. Whereas the rest of the materials I just talked about, methane, carbon monoxide, methane, methanol, or polymer, they're all below 200 to 600 million tons. So carbon monoxide can be a useful solution that we can make out of it. And where we are getting the carbon monoxide currently, we are actually slow burning the coals. And that means we are actually providing a huge amount of carbon footprint, not only because of the burning of the coal, but also from the mining of it. So if we can remove this carbon dioxide, make it carbon monoxide, so we are going to remove two ways the carbon dioxide from the atmosphere. One is directly, and one is the scope 2 carbon dioxide removal from the coal mining. So then we strategize how we can use it. So carbon dioxide to carbon monoxide is not something new in the industry. Industry is using it for a long time. They use that reverse water gas shift reaction. But that requires a huge amount of energy. The converter runs at 700 degrees Celsius or higher. That means we need to produce more energy connected to carbon dioxide footprint, so not really a very carbon footprint removal technique. So we wanted to do that at room temperature, where I can use the renewable energy, so totally carbon footprint free system. And that is our goal, to do that. And for that, we need a device which can do that. And there comes the carbon dioxide electrolyzer. So this is a basic setup of the carbon dioxide electrolyzer. It works same as the water electrolyzer. It has two sides. One, it does a reduction. Instead of hydrogen from the water, it is actually producing carbon dioxide to carbon monoxide, and this is a model of it. We made it out of acrylic so that we can actually see what is happening inside the black box. And this has 4 different components. One is a graphite material, which actually ensures that the material, that carbon dioxide we are putting in, it can flow at a particular rate. Then we have the catalyst, which actually does the reaction. And over there, we need 2 different catalysts, one for the carbon dioxide reaction, one for the water oxidation. And then we have to put everything together with a current collector, and that is how the system looks like. And over here, we have 2 terminals, which actually we need to connect it through the electricity, and then you purge carbon dioxide captured in a water, push it through that, it starts producing carbon monoxide. Then again, we need a proof that it is really happening. So the first proof comes over here. Yeah. So on this right-hand side, you are seeing this is actually an experiment called electrochemistry, where you can see it's a flat line, and then all of a sudden the line goes down. The line going down showcases there is an electron exchange. The reaction is happening. It is where the carbon dioxide is actually getting reduced. So that means carbon dioxide is interacting in this system. But how do I know it is a carbon monoxide coming at the end product? So for that, we collected the gas coming out after the reaction, put it in an instrument called gas chromatography, which can analyze what are the different gases present over there. And not only that, it can also quantify how much gas we have it. And over there, we found that we have carbon monoxide, and 67% of the gas output is actually carbon monoxide. And we also did how much energy you're actually using for production of this carbon dioxide to carbon monoxide. And we found whatever the energy we are putting in, more than 80% is actually utilized for this carbon monoxide conversion. And over here, we are providing multiple solutions. One, obviously, is that water-based solution, which can be scaled up. In the lab at this moment, we are capturing close to 100 kilos of carbon dioxide from the direct air. So it's a direct air capture unit, and converting it to the minerals. And the same aqueous-based system for capturing water we can utilize and connect it to this electrolyzer. And this electrolyzer over here can convert close to 1 kilogram of carbon dioxide in a few hours to carbon monoxide. And then we found that it is a very unique tool. So if I change this catalyst over there, we are not limited only up to carbon monoxide. We can do also other chemicals. And so far, we have tested 4 different catalysts, and we produced methanol, formic acid, and methane, which are all utilized in a large amount all around the world. And that gives us a unique template to convert captured carbon dioxide to unique chemicals that we require. And finally, we like to thank, as Bikram said, that it is a team of 6 who actually did all the work. So Somnath, Vaibhav, Shubham, and Piali are the other members who couldn't come here due to the time strain, but they are the unique, important key component of this team. And over here, after hearing to all of you and the initiative taken by OpenAir, I'm quite sure that we are looking for a greener and carbon dioxide-free future. Thank you. Thank you very much.
Next year, I need to rehearse putting medals on people beforehand so I don't mess up people's ears and stuff. Thank you so much for joining us to celebrate these amazing finalists. One more round of applause for these finalists. If you're here in person, we actually have displays over here from the teams themselves, posters and some prototypes, videos of their projects, so please come check those out. We also have a reception supported by the Tisch Institute for Creative Research, so help yourself to food and drinks in the adjoining room. If you're watching online, thank you so much for watching, and please tell everybody about how amazing these teams were, and we look forward to you joining us next year for the 2024 Carbon Removal Challenge. Thank you so much for joining us.